Hey everyone, today I want to talk about Inference Engineering 101. First of all, what is it? So Inference is essentially hosting and serving an LLM model. As simple as just like we have servers which are hosting a web application and serving a web application, Inference is serving an LLM model. But Inference is much harder. There's a lot of things that are going behind the scenes, which is a GPU running and the model, a GPU is running the LLM model, and imagine like billions of weights, like billions of model weights parameter model is running, and then it has to basically take the input prompt token and generate the next token, and then again the next token and next token, so on. So this is much more complicated, both from system engineering and much more interesting. First of all, why do we need to learn it? Three key reasons. I think one is that I sincerely believe that intelligence/LLM should be democratized. That means available to everyone on every device. And I think open source software is sort of leading the baton here. And with the kind of costs that we are seeing with frontier LLMs, more and more open source LLMs are becoming powerful and viable for production workloads. The second is the open source models, I think, will become like a backbone infra, something like open source software became. So there is going to be a special place for open source LLM models versus the closed source models. And I think it will become increasingly important to ensure that we understand what goes behind the scenes in hosting and running these models, because I see a multi LLM kind of future. So very lucrative and very important field to learn. And the last is that the future, I believe, as I said, is multi LLM. So it's right model for right task on right platform, which is like if I'm running on mobile, let's say on a mobile device and using it for some general purpose chat or web search, a very different kind of model versus something that I'm running on my computer, or I'm serving or I'm coding, or I'm serving some production workloads and so on. So if I'm running on laptop, if I'm running on a mobile device, if I'm running on any edge device, I think the right different kind of platform for different kind of task, there will be different kind of LLMs. So how do we make these LLMs work on different platforms is all about inference, and that's why it's so important to learn. So in this video, this is the Inference Engineering series where I'm learning and I'll be sharing more and more. In today's lecture, I want to discuss two things. One is behind the scenes in GPU, a very high level systemic understanding of when inference is happening, what is happening inside the GPU, which is what is running in data centers when we call LLMs. And we'll actually use Google's Collab, which has free GPU called T4. And we're going to run the open source Gemma4 12 billion parameter model, and we are going to run it and do inference and just measure like key parameters like time to first token, tokens per second, and so on. This is, I would say, slightly technical, but still keeping it very minimal and thinking it more like a system, because as an applied AI product manager as well as a product engineer, it becomes really important for me to understand, because these metrics, time to first token, tokens per seconds, and those things actually impact some of the very important metrics for my product, which is the performance that my customers are getting and the cost. And hence I believe that it'll be helpful to even the product manager audience as well who are working in applied AI. So let's start with the first thing in the agenda, which is behind the scenes in GPU where inference is happening. So when the LLM is serving or the inference is happening, what is happening in the GPU? So let's think of a very clear structure. Let's think of, like, normally what we do is what we have something called a client app, and we send a prompt, and then there is a GPU where the model is running, and then we get the more completed prompt, completed response. So let's say the cat sat on the mat, So here the response will be the cat sat on the mat and the next two words generated, which is and slept. So think of a very typical scenario that we are very used to. The first thing that happens is storing the model weights in VRAM. So a GPU has two core components. One is the GPU, the cores, which is basically all about your computations, your matrix multiplication, and so on. And the VRAM, which is earlier for people who are interested in trivia, it was called video RAM because NVIDIA started with focusing on graphics and so on. But there are two most important components. VRAM is where we store the model weights and everything. And there are some other things like KV cache and so on. And cores, GPU cores, where the computation happens. And think of a wire that's connecting them, that's moving data back and forth. And this is what's called bandwidth. So how many GBs per second you can move the data from the VRAM to the computation. So these three things determine a lot about inference. So think of the first thing that you have a Google Gemma4 12B model, which is 12 billion parameter model. And for each parameter, we are just taking 4-bit. Usually it is 16, but let's say it's a smaller model. We want to run it in a cheaper GPU, so it's like 4-bit. So there's this formula that, let's say 12-bit into 4, which is 12 billion parameters into 4, because for each parameter we're taking 4-bit divided by, so that's almost 6. So 6 GB worth of VRAM is what will go into these model weights, and almost we add like 25% more. So if you have like a Gemma4 12B kind of a model, you need at least close to 10 GB of VRAM in the GPU. And that's how you can think of like what model you're running and what hardware you have and so on. Then the second thing that happens is tokenizing the prompt. As we know that LLMs do not understand words, they understand tokens. So each word goes through a tokenizer, and essentially the prompt is converted to token. And then starts the two most important phases, prefill phase and decoder phase. Decoder is where the tokens are generated, the next token, the next token, the next word that is generated. But before that, there's something called the prefill phase. Because for each of the tokens in the input prompt, the model is loaded from the VRAM and it generates something called attention score. And if you know, that whole transformer architecture got evolved from the attention mechanism, and that's why like for each of the tokens in the input prompt, it has to create attention score, and it is stored as a key value or as a KV vector, and it is stored in the KV cache, which is in the VRAM. Now this what it does is, in this prefill phase, is we load all the model weights one and parallelly generate tokens for each of the input, generate KV vectors for each of the input tokens or the attention scores. And that's why it's a very compute bound kind of an operation. So what compute bound means, that let's say your prompts is really big, and in typical RAG pipelines you have bigger and bigger prompts. So the more compute that is available with the GPU, the faster you can do finish this prefill phase and start into your next phase of the word prediction or token generation. That's why it's called compute bound. So imagine that this whole input prompt / converted into tokens is processed, and something called attention scores that is created for each of these tokens, and they are stored in this KV cache because they need to be referred. And then starts what we call prediction, which is the next token generation, or the next word prediction. So after here, the next word prediction is going to be and. But remember that LLM works in tokens, so almost 1.5 words and not in like English words. So in the decode phase, what happens is, and this is where it gets interesting, because you can only do prediction word by word or token by token. You cannot generate like 10 tokens at a time. So this is a very heavy on the bandwidth bound kind of phase where you load the model weights, you look at the KV cache, and you generate the next token. You run the model, and it's like a deep learning model. So you do a forward pass and you generate the next word or the next token. Now the computation is very less, just next token, but you have to load all the weights from the VRAM. The next token is generated, its KV vector is created, attention score is created and saved, and then again the model is loaded and the KV cache is loaded, and the next token is generated, and the next token and the next token. So it's a very sequential process, and that's why it matters a lot on how fast the data can move from VRAM to core. And that's why it's a bandwidth bound process, and depends a lot on the bandwidth, how fast you can generate the next token, and it starts impacting your tokens per second. So now this is what is fundamentally happening in when your LLM inference is happening, or the token generation. So you tokenize the prompt, you do a pre-fill pass at the input prompts or input tokens, and it essentially creates something called KV vectors with their attention scores, saves it in a cache to refer later in the decode phase. And the decode phase is where you move the model and you run it, you generate the next token, and then you save it in the cache, and then again the next token and the next token and the next token. Why? And a lot of these companies like Fireworks, Base 10 and so on are optimizing this whole process for faster inference and for production workloads, and there's a lot of systems engineering that goes into it. But why is it important as an applied AI PM to understand this is it directly impacts your two key metrics. One is performance and second is cost. Performance starts with your customer's perception, starts with time to first tokens. If you are streaming response, the time to first token depends on what is the length of your prompt. Then it depends on what kind of GPU system that you have, what kind of model that you have, how much time it is going to take in the pre-fill phase, depends on the length of the prompt and how fast it can do the computations. And then only after pre-fill phase, it will start the token generation, which is like the prediction phase, when you start receiving the metrics, start receiving the predicted tokens. That depends on the bandwidth. So you have these 3-4 parameters with which you can play around to see how fast you can generate the first token. And prompt caching, so think of like the what happens is that if you send the same sub portion of the prompt every time, today's production workloads or inference systems are smarter that they keep this KV cache for some time. And essentially, if you send the next prompt and the next prompt, and it is your system prompts have the same words, it essentially means the same tokens and the same attention scores. So it can reuse that scores instead of computing it again. And that's why prompt caching is one of the very prominent techniques of both faster performance as well as saving some dollars. And tokens per second, as we said, depends on, in your decode phase, how fast you can move the data to generate the next token. So this is what happens when you basically send a prompt and the token starts generating. And as an applied AI person, if we understand these 4-5 parameters, we can ask the right questions to our engineering teams or to our inference team and see what we can do better. And I believe a lot of companies are coming here in this particular phase and are optimizing this architecture for faster inference for at a reasonable cost. Now let's go into the second step of the agenda, which is hosting and running a Gemma4 12B on a free T4 GPU instance in Google Collab. This is where we go into practical from theory, and we'll record time to first tokens, token per second, those kind of metrics. So I hope you can see my Google Collab. Right now a lot of code is written by Claude, so you don't have to, and I'll be publishing it using on GitHub. But essentially, this is a very interesting practical of whatever we learned in theory. So we have a Tesla T4 GPU, and this has total VRAM. If you remember, we talked about uh, VRAM here, which stores the weights and the KV cache. So that's almost like 15 GB, and we are going to load the model weights, which is Gemma4 12B. So we roughly calculated 6 GB of model weights, and we are going to use Hugging Face libraries like transformers, which is basically helps a lot with storing, basically loading these models and inference and so on. So here we are loading the Gemma4 12B model, and I set 4-bit quantize, which is we are to fit into this GPU. We are using the 4-bit precision versus 16-bit. So there's a library called bits and bytes config, which basically allows you to do like a 4-bit quantization. So we are saying that we want to load the Gemma4 12B model, 12 billion parameter model, but we want to load the 4-bit quantized one. And as I talked about that tokenizer, so there's auto tokenizer. It looks at the model and loads the tokenizer, and finally the model is loaded. So this takes almost 10 minutes, and it essentially loads the model, which is 4-bit quantized and Gemma4 model. So now let's see the RAM snapshot after loading. So we had predicted approximately 6 GB for the model weights in our VRAM. It's taking close to 7 GB, and that's because apart from the model weights, there are some quantization and certain other things are also stored. So we have like from our 15 GB VRAM, 7 is gone, and now almost 7 is left. So here's a slide. This is only for visualization. So you can see half of the VRAM is gone, and if you see here, almost 40% of this 7 GB, almost 5.6 GB is your model weights, and the other things are CUDA kernels. These things are quantization metadata. All these things are taking the remaining 1.5 GB. So we were very correct. Almost 6 GB is what we predicted the model weights. It's actually 5.6. So now let's do inference, which is we give it a prompt, and we measure the time to first token and the tokens per second. Decode speed is tokens per second, token generation. So here we send this prompt, explain how the transformer attention mechanism works in simple terms. This is the prompt we are giving, and it will basically, we are right now generating only 200 tokens maximum. So if I run this, so you can see that I have this prompt is converted into 24 tokens. So this is the prompt tokens, input prompt tokens, and the generation is still happening. So I'm waiting for prefill phase to complete, the model weights to be loaded, the prefill phase, I'm waiting for this prefill phase to complete, and then finally the decoder phase to happen, and then the response will come. Great. So now my inference is complete. So I see that 24 tokens were the input prompts. I had limited output tokens to only 200. So let's see the model response. So we had sent this prompt, explain how the transformer attention mechanism works in simple terms, and this is what it generated. To understand the transformer attention mechanism, it helps to start with a simple analogy how human processes sentences and so on. Right. So let's see some metrics. Time to first token, so almost 1.2 seconds. And the decode speed, which is your token generation, is roughly 4.7 tokens per second. That's very slow. And obviously because this is like a basic GPU, and and essentially we are doing like raw inference. We'll see in the next lecture how if we use an inference engine like llama.cpp or something, that it gets better. But this is essentially what the metrics are. So we talked about time to first token, we talked about the tokens per second generation, which is the decoder phase or decode speed. And if you can see the VRAM, right now KV cache is very low because we sent a very small prompt. So it's like 0.01 GB and almost 7 GB. So this is there. Now what we can do is we can, this was the base prompt. So we'll run a slightly larger prompt, and we'll see if we run it more, how the VRAM grows. So basically I'm going to send here the base prompt, and there are different input tokens, like the prompts will be increased, the words will be increased, and so on, to see if I keep changing the prompt length. So it's like an ablation study of different prompt lengths. How does it impact the VRAM storage and the token prediction speed and so on. So as you can see here, with 45 prompt tokens, it's roughly 376 time to first token in milliseconds, and tokens per second 5.71, and VRAM 7.29. This roughly remains the same, only the KV cache is increasing. So as you see here that 45 versus 269 almost doubled our KV cache, where we were storing the KV vector for the tokens. And roughly our time to first token, you can clearly see that the time to first token is linearly scaling here, but the tokens per second roughly remains the same. So essentially, as we discussed, that the more the prompt, the bigger the prompt that is going to be, the more the prefill phase is taking the time, the more our time to first token is increasing. But once we go into the decoder phase, which is the token generation, then it is taking roughly the same, because it is dependent on the bandwidth to generate tokens per second. So that's, I think that's pretty clear, and our KV cache is also increasing. So if you see here, like time to first token is basically linearly scaling. So ensure your prompts are optimized so that you get faster responses, whereas your tokens per second roughly remains the same. So that does not change. That's about it for today. So just quick recap of what we did. We talked about inference engineering. We talked about what does it mean, why we should learn it. I think it's a very, very interesting space. And the two things we learn is, at a very high level, what happens in the GPU where inference is happening. And then we actually hosted Google Gemma4 12B on a T4 free T4 GPU instance on Google Collab, and we ran it. We did inference. We loaded from Hugging Face, and we actually measured time to first token, tokens per second, and how with the input prompt, time to first token linearly scales while tokens per second roughly remains the same. In the next lecture, we are going to take a more powerful GPU called A100 and in the Collab Pro, and then we are going to do a similar experiment and see what a powerful GPU does better, which has more VRAM, more bandwidth, and so on. Till then, thank you.